Good morning, everyone. Welcome to the Algebraic Graph Theory seminar. Today it is my pleasure to introduce Sho Suda from the National Defense Academy of Japan, and he's going to speak about symmetric and skew-symmetric signing of graphs.
Yeah, thanks for introducing, and I thank the organizers of this seminar for inviting me this. I'm going to talk about symmetric or skew-symmetric signing of graphs, and this talk is based on joint work in progress with the two professors, Hadi Karagani and Jack Coren. So, first of all, I'd like to define the signing of graphs. So maybe many of you know this concept, but I will start with its definitions. A signing of graph is the is just a mapping sigma from the Cartesian product B times B to the set consisting of the three elements 0, 1, or -1, satisfying the following two properties, and the sigma of x, y is not equal to 0 if and only if the two vertices x and y are adjacent in our graph G, and sigma xy is equal to sigma yx for any two vertices x and y. And we call this signing as symmetric, but I don't often use this term, but we call this pair G and sigma signed graphs. And likewise, the usual algebraic graph theory, we can define the signed adjacency matrix denoted A sigma as follows. And it's a square matrix of order phi whose column and rows are indexed by the elements of the vertices, and with xy entry equal to the sigma of x and y. And for example, if we look at this picture, this is the signed graph with the underlying graph G being C4 and the cycle on 4 vertices. And if we assign the values for each edges, like this way, 1, 1, 1, and -1, so one of the 4 edges receives negative entries, and we call this as the signed graphs. And we can define the signed adjacency matrix from these graphs, and with some ordering of vertices. And as it feels, if we the labels 1, 2, 3, 4 here, we can define its signed adjacency matrix. So exactly the same way as the usual adjacency matrix. And here 3, 4 entry and 4, 3 entry appears as -1. And we want to work on this matrix, signed adjacency matrix, in this talk. And signed graphs topic started maybe around 40 years ago, and Zaslavsky started this topic to study, and the title of this paper is just signed graphs. Also, Zaslavsky also famous as in the theory of spectral designs, as his work on the existence of the spectral designs. So anyway, so he also works on this topic, signed graphs. And also, the second one is the recent survey by these four guys, big guys, Berardo, Shelba, Coren, and Wang. The title of this paper is Open Problems in the Spectral Theory of Signed Graphs, written in the almost 7 years ago. So many topics about the spectral theory on signed graphs appeared in this survey paper. So this is quite a nice survey, so we can get many information from that. So in this talk, I'm going to think of the spectral radius of the signed adjacency matrix. And throughout this talk, G sigma via signed graph is signed adjacency matrix A sigma, and we consider its signed adjacency matrix. We consider the spectral radius of this signed adjacency matrix G sigma. This is just the spectral radius of the corresponding signed adjacency matrix. That is the maximum of the absolute value of eigenvalues of the signed adjacency matrix A sigma. And as I said, we would like to focus on the spectral radius of the signed graphs. Now, why is this important? And actually, if we consider the so-called two-rift of the signed graphs with small spectral radius, can be used to construct bipartite Ramanujan graphs. So that's why this the signed adjacency matrix with small spectral radius is very, very important in this topic. And I want to review the known result for this construction. And also, I would like to define the two-rift for the define the two-rift of signed graphs. And if we decomposed signed adjacency matrix A sigma as the linear combination of the A1 and A2, where A1 and A2 are disjoint symmetric 0-1 matrices, it means they are the adjacency matrices of some graphs. And we can easily realize that the matrix A, which is defined as the sum of the two matrices A1 and A2, and this is the adjacency matrix of the underlying graph of G. And the two-rift of a signed graph, G sigma, is defined like this, which is the graph denoted by G tilde, whose adjacency matrix is defined to be this way. So A tilde is has the 2x2 block forms, and 1 block and 2 blocks are equal to the A sub 1, and 1 block and 2 blocks are equal to the A2. So for example, if we take this signed graph on C4, so we can construct undirected graph G tilde and like this, and G tilde has and we consider the two copies of the vertex set of the original signed graphs, and then we define the edge set on this. And if edge receives the positive value 1, then these two vertices connected in each layers in the resulting graphs. And if two vertices receive the negative values -1, then we connect edges between two vertices in different layers. So this is the two-rift for the signed adjacency matrix. And we can easily prove this proposition using this matrix form. And this proposition claims the set of the eigenvalues of the resulting graphs adjacency matrix is equal to just a union of the eigenvalues of the adjacency matrix and eigenvalues of the signed adjacency matrix. And here we consider this set and this union as in the merge set. So if we know all the eigenvalues information of the adjacency matrix A and its signed graphs eigenvalues, and we know all of the eigenvalues of the resulting graphs and with its multiplicity. So, so for the spectral radius, as we know about these two, and in this talk we use this notion rho g sigma, which is defined as the spectral radius of the signed graph g sigma, and this was conjectured by Bill Linear in 2006 in the paper appeared in the Combinatorica, and let G be a k-regular graph. And I didn't write, but the k must be at least 3. And for any k-regular graph G, there exists a signed graph G sigma, or there is a signing sigma on G, such that its spectral radius of the signed graphs is at most 2 times square root k minus 1. So this value 2 times square root to k minus 1 appeared, of course, the Ramanujan graph's definitions. So Ramanujan graph is as you know, just a k-regular graph. such that the any eigenvalue, theta, which is different from k and minus k, satisfying its absolute value is at most 2 times squared k minus 1. So Ramanujan graph is one of the main important object in the graph theory, and many people, I think, they try to construct this object. And so 10 years ago, these three guys that prove this nice result about the signing. So they prove for any k-regular graph G, there exists a signing sigma such that the maximum eigenvalue is just a maximum eigenvalue of the signed graph G sigma is at most the desired value 2 times squared k minus 1. So they can claim they can control only on the maximum eigenvalues, but not the least eigenvalues. So they didn't claim anything about its spectral radius. But if we apply this theorem to the bipartite graph G, so they succeeded to construct bipartite Ramanujan graphs from any bipartite regular graphs. And I think that before that, Ramanujan graphs construction so heavily based on using the finite fields, but their proof for the construction of the Ramanujan graphs is the finite field free. So this result is very surprising, and also their technique, so-called interlacing families, I think is now much famous, and many people are using this concept to apply some other areas, I think. So that's why the spectral radius is very important in the theory of the signed graphs. So in this talk, I want to show our result, and they are divided into 3 parts. And first one is the improving a lower bound for spectral radius for no lower bound, but I didn't mention its lower bound yet, but I will explain this one in a few slides next. And also, I want to give some examples of signing for just a specific graphs with smallest and spectral radius or relatively small spectral radius. And here, relatively small means our signings satisfying the Beer-Linear's conjectures. Also, I want to introduce the skew-symmetric signing, and also I want to give some result about the skew-symmetric case. So, in order to show our first contributions, and I will show you some known result for the lower bound of the spectral radius. So according to the survey paper by Big Four guys, and this theorem was proven in 2012. But I think many people already know this theorem, or you can easily prove this theorem and without seeing its original proof. And this theorem is giving some lower bound on the spectral radius for any signed graphs, and its lower bound is the square root of the average degree of the underlying graph G. So square root of the sums of degrees and over the number of vertices. So this is the lower bound for any signed adjacency matrix. And also the equality case is completely described. Equality holds if and only if and signed adjacency matrix must be a Wang matrix. And here, Wang matrix is just a square matrix with entries 0, 1, or -1, such that any distinct, such that there is a positive integer k satisfying W times W transpose is equal to k times identity matrix. And here, this integer k is said to be the weight of the Wang matrix. So I started this work and maybe 3 years ago when Jack Cohen visited me and whenever I met him and he proposed some research problem and he showed me something and so maybe Jack Cohen's in his mind and so this lower bound is closely related to my research area because I have been working on the wave matrix from the viewpoint of the algebraic combinatorics or algebra and association scheme. So that's why maybe Jack Cohen introduced me to work on this topic. And, and I want to show some example attaining the bound. So for example, complete graph K and K's, the optimal signing, it means the signed adjacency matrix attaining this lower bound is just a Wang matrix of order n and weight n minus 1. Now, this object is also known as the conference matrix. This is also very famous object in design theory. And for complete bipartite graph KNN case, the signed adjacency matrix attaining the Gregory's lower bound is just this type of matrix, zero matrix, some 1 minus 1 matrix H, and its transpose H transpose and a zero matrix. And where this H is a Wang matrix of order n and weight n. And then this object is also known as the Hadamard matrix of order n. And then these two objects, and also, of course, the Hadamard matrix is very, very, very important object in design theory. So these two important objects appeared in the spectral graph theory in natural way. Also, two more examples I want to show you. The first one is the signing for binary Hamming graphs. It's just hypercube. This graph has a signing such that its signed adjacency matrix becomes a Wang matrix. And as you know, this signing was used in proof of so-called the famous conjecture, sensitivity conjectures. And this result, appeared in the Annals of Math already 6 years ago. So I think that we are really surprised. So this signing is also very famous in our community, I think, but this can be used in the prove some conjectures. And the last one is our first contribution to this theory, signed adjacency matrix, signed graphs. And we found some signing, and it is a Wang matrix, and whose underlying graph is so-called divisible design graphs with specific parameter. Here, 6 values here. So I want to show what is the divisible design graph and what is our construction. So divisible design graph is with parameter vkmn lambda 1 lambda 2 is a graph with the adjacency matrix A satisfying this matrix equation. If we consider the A square, this matrix can be written as a linear combination of the identity matrix I sub V and tensor product I and J, where the order of the identity matrix here is n, and the order of the all ones matrix here n, and also all ones matrix of order phi. So this condition, for these conditions, m times n must be equal to this value v, and k appears here, the coefficient of I here, and lambda 1 and lambda 2 appears the coefficient of the second term, and lambda 2 appears the coefficient of the third term. So this concept was introduced by the Kalgani and Hemers maybe more than 10 years ago, and he constructs and studies this topic Yes. And theoretically, and they gave many examples of this divisible design graphs. And we want to find and signing for specific divisible design graphs. In order to do so, we use so-called balanced generalized Wang matrix. So this is somehow complicated concept, but it's a generalization of a Wang matrix. So in order to define this object, we need some finite group G, which is multiplicatively written finite group. And this group does not contain some symbol 0. And balanced generalized Wang matrix with parameters vk lambda over this group G. And in this talk, we denote this object as BGW vk lambda over G is a matrix W of order phi with entries from this set 0 and the union of the 0 and the finite group G, satisfying two conditions. The first one is every row of our matrix W contains exactly k non-zero entries, and for any distinct I and H taken from this set from 1 to phi, so every element of G has exactly lambda over the size of G copies in the merge set of this one. So this set consisting of the element Wij times Whj inverse, where Wij is the ij entry of our matrix W, where J runs from 1 to V, and Wij is not equal to symbol 0, and Whj is also not equal to 0. So this concept is so complicated. So if you look, and here is an example of maybe the non-trivial smallest one, I think. In this case, the finite group G is just the cyclic group of order 3. And here we use U as its generator, and BGW with parameters 5, 4, 3 is the following. And 5 means our matrix has 5 by 5. And 4 means every row contains 4 non-zero entries. And 3 means and if we consider the first row and the second row, and if we consider this set, Wij and Whj inverse, here we consider the W1j and W2j inverse, where j runs from 1 to 5, and this set consisting of the I, U, and the U square, where I is the identity element of our group. So the lambda must be, and each element appears exactly one time, so lambda must be the order of finite group G. So so 3 appears here. So here is the non-trivial smallest example of, I think, BGW. So also you can realize this matrix is symmetric, and the 0 diagonals and ij entry is equal to 0 entry. So this BGW is symmetric. So this is just a coincidence. And so there are so many works on the BGW, so mainly on construction of the BGWs. So this using the finite field. So this theory is known. So for any prime power q, which is congruent to 1 modulo 4, there exists a symmetric BGW with this parameter set 1 plus q square, and q square minus 1 over the cyclic group of order 2 plus 2q. And in this case, the generator is so we can take any generator, and in order to construct our divisible design graphs and with the nice signings, we take as the generator as the negative matrix of order 1 plus q, where negative matrix is the definition is here, but if you look at the right-hand side example, so you can understand its definitions. It's like a shift matrix, but the n1 entries is not equal to 1. So we replace just 1 with negative 1. So this is the negative shift matrix of order 4, and of order n case, and here is the definition. And in our BGW, so we use this negative shift matrix as a generator. And so let us take W as such a BGW with desired values and desired generator matrix. And also we use so-called back diagonal matrix denoted R of order 1 plus Q. And the back diagonal matrix is the permutation matrix and whose ij entry is equal to 1 if and only if, and I plus j whose ij entry is equal to 1 if and only if I plus j is equal to order plus 1. And in this case is from the rightmost entries to the left below entries, so there are ones. So this diagonal is not main diagonal, but we call often this diagonal as the back diagonal. So we call this matrix as the back diagonal matrix. And using this our BGW and also using the back diagonal matrix, we define A tilde as this one. And it's a block matrix whose ij entry is equal to the ij entry of our BGW times back diagonal matrix R. Then it's routinely proven that this matrix A tilde, and this is the 0, 1, minus 1 matrix with 0 diagonals, and symmetric, it's also a symmetric rank matrix of order some value and weight some value. And also, if we replace entries minus 1 with 1, this resulting 0 matrix is the divisible design graphs adjacency matrix. So this is our construction for the symmetric rank matrix, and whose absolute matrix is becomes some nice graphs. So the construction is somehow complicated, but we can construct some nice signing for some nice object in algebraic graph theory. So far, we are working on the Gregory's inequality, but as you realize, the symmetric rank matrix is really rare object, so it is desired to improve his lower bound for spectral radius. And the second contribution of this talk is showing this one. G sigma is same as before, just sine graph on n vertices with spectral radius rho G sigma. And in order to claim our inequality, we use this value t. So t is counting the pair two vertices x and y, such that the x and y are different vertices, and the size of the common neighbors from two vertices is odd. Then we have and we can improve the Gregor's inequality this way. So the spectral radius is at least this value. And inside of the first square root, the first term is exactly same as the Gregory's one, but the second term, the square root inside of the square root. So this value is certainly non-negative. So this inequality is better than the Gregory's one. And I didn't give a proof in detail, but I want to share with you the sketch of this proof. And we consider the eigenvalue of our square of our signed adjacency matrix, and just applying some old result shown by these two guys, maybe more than 40 years ago. So I think this result appeared in the statistics. So roughly speaking, these two guys proved the four real numbers, n real numbers, x1 to the xn, and the maximum value x sub 1 is at least the average plus some variance. So just applying this result to our case, so we found and we can conclude our the improved lower bound on the spectral radius of signed graphs. So also we can characterize the when equality hold. And the equality hold in our inequality if and only if there is a positive integer k and some monomial matrix P such that the square of this matrix P times A sigma times P transpose has nice block form. So 2 by 2 block forms. So 1 block is the k times ik minus jk. The ik is the identity matrix of order k, and the jk is the all-ones matrix of order k. And the 1-2 block and the 2-1 blocks are the zero matrices, and 2-2 blocks is the k times identity matrix of order n minus k. So so this is somehow this is something similar to the Wang matrix conditions, and after I proved this theorem, and I realized these two guys, Gary Greaves and Duran Stanich, prove the following: some 0, 1, minus 1 matrix A sigma is a signed adjacency matrix A sigma satisfies this matrix equation if and only if this bordered matrix becomes a Wang matrix of order n plus 1 and weight k, and of course with zero diagonals, and for some column vector x with entries from 0, 1, minus 1. So this claims this is not Wang matrix, but this is very close to the Wang matrix. So their theorem says to obtain the optimal object of our inequality, extremal object in our equality, just deleting the rows and corresponding columns from the symmetric Wang matrix with zero diagonals. So but anyway, so we can improve the Gregory's inequality for spectral radius. So this form is somehow complicated, so I want to show you some straightforward corollary from that. If we apply the Gregory's result to the complete graphs, we can claim, so for any signing on complete graphs, its spectral radius is at least squared n minus 1. And as I said, with equality if and only if it becomes the conference matrix. And the necessary conditions of the existence of the conference matrix, the order n must be even. So it means for n odd, we don't have any example attaining this lower bound, but for n odd case, so we obtained, if we apply the n odd case, the spectral radius of the signed complete graph is at least a square root of n, little bit improved, and with equality holds if and only if there is some monomial matrix P, such that the P A sigma times P transpose is equal to Ni minus J. So if you know the construction of the Hadamard matrix from finite field, so this condition is exactly same as so-called core matrix. So in order to construct Hadamard matrix, we consider the some core matrix using the quadratic characters, and then we fill and one column and one rows to become a Hadamard matrix or the conference matrix. And this, in our case, and same things happened. So this is the corollary of our result, but in this slide, I want to show you some computer search for smallest spectral radius for uh, some strong regular graphs and some dissonance regular graphs, maybe diameter 3 with small valencies. I think they all are not Wang matrices, but and I'd like to mention that the all smallest spectral radius signing satisfying the bilinear conjectures. Okay, so I want to so before that um I gave in that table I gave the smallest and spectral radius signings for small examples, and so moreover we can find some nice signing but not optimal. It means our in this slide and in the next few slides we don't have a symmetric Wang matrix, but and our signing satisfies bilinear conjecture. Now here I want to show you three examples of such nice signings. The first one coming from the symmetric Hadamard matrix with constant diagonal 1. If we subtract the identity matrix from that, this can be regarded as the signings for complete graph on 4 times n square vertices, and we can explicitly calculate its spectral radius, which is equal to 2n plus 1, and also this, our signing, satisfies bilinear conjectures, and also we can use some Hadamard matrix with more properties, so-called symmetric and Bush type conditions. I don't go into detail, but this is also famous object in design theory. And from this matrix, if we consider the H minus I tensor J matrix, this can be a signing for complete multipartite graphs with the spectral radius 2n, and also I didn't show you the exact calculation, but see this satisfies their conjecture. And also likewise the divisible design graph case, and we can find some example of the strong regular graphs with these 4 parameters, and whose there is some signing satisfying and bilinear conjecture. In this construction, in our signings has the spectral radius at most q plus square root q, and we couldn't find exact value of the spectral radius, but we can give an upper bound of our signings for the spectral radius, and it satisfies their conjecture. Also, 2 more slides, I would like to mention uh, Johnson graphs case and Hamming graphs case. And very recently, these 4 guys upload their nice paper on archive, and they are working on the signing on distance regular graphs. And one of their beautiful theorem is there is a signing of Johnson graph JVD, and which has the only 2 distinct eigenvalues, d and minus phi minus d. So this preprint deals with the signing of graphs with the smallest number of distinct eigenvalues, not considering about the spectral radius, but they consider the smallest number of distinct eigenvalues signings. And in Johnson case, so they could find very nice signing. Its sign adjacency matrix has only two eigenvalues. And the calculation shows that their signing satisfies the linear conjecture if these, at least this value, so roughly the V over 5. So we still don't know the small d case. We don't have signing satisfying for Johnson graphs satisfying bilinear conjecture. So it would be really interesting to think of this case for Johnson graphs with small d. Now also, this is the small observation for Hamming graphs. So for Hamming graphs, we can consider some nice signings using the conference matrix. So let's see a symmetric conference matrix over the Q with the diagonals and then define Q to the n times Q to the n matrices A sub n. So recursively by this way. So initial term is A sub 1 is equal to the symmetric conference matrix C, and A sub n plus 1 is defined to be the sum of I tensor n plus C tensor some identity matrix. Then, so we can explicitly calculate its eigenvalues of this matrix A sub n. It's a multiset, and eigenvalue is the n minus 2i times square root q minus 1, and exponent is of course its multiplicity, and we can determine its spectrum with eigenvalues and multiplicity explicitly. So this calculation shows the spectral radius of our signing for Hamming graphs is equal to n times square root of q minus 1. And as you know, the Hamming QRA Hamming graphs valency is equal to n times q minus 1. So we can check whether our signing satisfies their conjecture. So actually, if n is equal to 2 or n is equal to 3, and we can claim our signing satisfies their conjectures. So just a strong regular graphs and diameter 3 case, we have a nice signings, but we don't know. I don't know the Hamming graphs of diameter larger than 3. So it would be also interesting to think of the nice signing for Hamming graphs. So finally, I want to move to the last topic, so-called, which I want to call the skew-symmetric signings of graphs. So this is just a variant of the symmetric signings, just changing the second conditions here. Sigma xy is equal to minus sigma yx. It means the resulting adjacent signed adjacent matrix becomes skew-symmetric. So that's why I want to call this concept as a skew-symmetric. But this skew-symmetric signing is exactly the same as considering orientation of the undirected graph edges in our graph G. Also, yeah, this is the definition of the skew-symmetric signed adjacent matrix, as you guess. So also in this case, we can define the two lift of the graphs. And from skew-symmetric signings, we can decompose its signed adjacent matrix, skew-symmetric signed adjacent matrix, as a linear combination A1 and A2, where again the A1 and A2 are disjoint 0, 1 matrices. It means the 0, 1, 0 matrices and also symmetric. So these two are, sorry, not symmetric, but the A2 is equal to the transpose of A1. And also, this sum, A1 plus A2, is the adjacent matrix of original graph G. And if we say the two lift of signed adjacent skew-symmetric signed graph is the undirected graph whose adjacent matrix is defined like this. Here, for example, this is indeed symmetric because if you look at the 1, 3 entry A1 and 3, 1 entry A2, then as I said, the A2 is equal to A1 transpose, so this becomes a symmetric 0, 1 matrix with 0 diagonal. So this is the adjacency matrix for some graph. Also, we can calculate its spectra, a tilde, which is written like this way. It's just a union of spec of A and spec of negative A and spec of square root minus 1 times A1 minus A2. And this A1 minus A2 is the skew-symmetric matrix with real values entries. So all of the eigenvalues is purely square root minus 1 times real number. So if we multiply this value, so this eigenvalues belonging to this set it becomes real. So spec A tilde can be written as this way. So also just same as before, and for skew-symmetric signing, we can conclude we can derive the lower bound. So the first inequality corresponding to the, of course, Gregory's inequality, and also the same lemma can be applied to skew-symmetric case. So we also obtained this second lower bound for spectral radius of skew-symmetric signings. And also, the characterizations for both cases are exactly the same as before. But of course, A sigma is in this case, first case, is the skew-symmetric Wang matrix. And also, in the second case, something different from previous one, but this case, P times A sigma by A sigma transpose by P transpose is equal to the desired block form. So finally, I would like to give you some nice skew-symmetric signings for graphs. So actually, I could find these signings first and then try to generalize the skew-symmetric signing. So in this case, we consider the adjacency matrices A sub n defined by this recursion. So where n start from 3, so A3 is equal to the J4 minus I4, and A sub n plus 1 is defined to be ANI, It's a 2 by 2 block forms, and the main diagonal are equal to A sub n, and the off-diagonal blocks are equal to the identity matrix. And we can claim that the graph whose adjacency matrix is equal to this one, 2 by 2 block form, and 0, AN, 0, and the main diagonals are the 0 matrices, and the off-diagonal blocks are equal to A sub n, is the corresponding to the hypercube on 2 to the n plus 1 vertices, so having graphs Hn plus 1, 2. So we can consider the signing for graphs of AN. So A sub n is the adjacent matrices of some graph. So we can, so now I want to think of the signing of these graphs. So to do so, we consider these, we use these two matrices, B sub 3 and R sub 3. And B sub 3 is defined like this. This is the skew-symmetric conference matrix of order 4. And also R3 is a diagonal matrix whose diagonal entries are the 1 minus 1, 1 minus 1. And for the n plus 1 signings, it's defined by this way, B sub n, R sub n, and the negative Rn, and the sum matrix minus Rn times Bn times Rn. Also, we consider this signed identity matrix. One block is just the R sub n, and 2 blocks is equal to minus R sub n. Then we can claim for any number, any n, at least 3, this matrix, 0, 1, minus 1 matrix, Bn, is a skew-symmetric weight matrix of order 2 to the n minus 1 and weight n. And also this matrix, B sub n, gives a skew-symmetric signing of the bipartite half of the hypercube, whose adjacency matrix is A sub n. So it means our skew-symmetric signings gives another optimal signings for the Hamming graphs, hypercubes. So I think this is some interesting signings, skew-symmetric signings in the classical object. So I want to think of the more about the bipartite half of the famous graphs. Now, whether it has the skew-symmetric signings, which becomes the skew-symmetric rank matrix. So finally, I want to share with some open problem related to my talk. The first one is I want to think more about it would be desired to give more constructions, symmetric or skew-symmetric rank matrices with 0 diagonals. Also, it would be interesting to find signings of graphs with minimum spectral radius. Also, I didn't mention anything about it, but so nowadays many people working on so-called coherent closure, which is coherent configurations of some metrics. It is the smallest coherent configurations contains the original matrix, and maybe studying the coherent closure of signed graphs and with or without smallest spectral radius would be interesting, I think. So for example, the Johnson graphs case, there is a nice signings of Johnson graphs. So what is the coherent closure of this signed Johnson graphs? It may be some other association schemes. I don't know, but it would be interesting. Now, finally, I want to emphasize it would be interesting to generalize some works to the quaternary case. It means the signings. And so each edge assigns these 4 values plus minus 1 or plus minus square root minus 1 entries. And I think the Mohana Go studies the Hamish adjacency matrix. So this quaternary signing related to this matrix, Hamish adjacency matrix, and also quaternary equiangular lines. Also, the quaternary rank matrices and the quaternary Hadamard matrices should appear in this framework. So I want to think more on these 4 topics later. Okay, so this concludes on my talk. Thank you for your attention.
Thank you very much. So, are there any questions? Yeah, I have a question. You write generalized to quaternary signing. So have you considered, for example, other lifts instead of 2 lifts? So for example, 3 lifts of graphs, which I think correspond to putting roots of unity instead of plus or minus 1. So do you have results about that or as well?
No.
No.
So I think maybe Gregory's inequality can be generalized to this case, but I don't know our improved lower bound. But also, as you know, the third root unity case conference matrix, and there exists such object, so there should be a optimal object in this setting. So it would be also interesting to think more third root unity case.
Okay. Thank you.